Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome to guest lecture of the Agricultural and Biosystems Engineering. This guest lecture with the title of Near Infrared Spectroscopy Principle and Application in Agri-Food Products. First of all, let me introduce myself. I'm Hafiz, student from Agricultural and Biosystem Engineering. Gadjah Mada University will be today's event MC. This event is part of weekly series of workshops that are held twice a week to be a part of implementation of independent campus competition program with agricultural and biosystems engineering partner. Therefore, we will get to know more about agricultural technology and gaining various benefits. So, don't miss out on participating in every series of this workshop. Sebelum memulai rangkaian acara kuliah tamu ini, izinkan saya untuk menyampaikan beberapa tata tertib yang harus dipatuhi selama kegiatan ini berlangsung. Pertama, peserta diwajibkan hadir 10 menit sebelum acara dimulai, yakni pukul 14:20 waktu Indonesia Barat. Kedua, peserta wajib menggunakan format penamaan, yaitu instansi _ nama lengkap. Dan untuk mengubah format penamaan tersebut, Anda dapat menekan tombol di pojok kanan atas pada partisipan list, kemudian tekan more, lalu tekan rename dan isikan sesuai format yang diinginkan. Ketiga, peserta diharapkan menggunakan virtual background yang telah disediakan panitia selama sesi kuliah berlangsung. Keempat, peserta diharapkan untuk mengaktifkan video selama sesi workshop berlangsung. Kelima, peserta wajib menonaktifkan suara selama sesi workshop berlangsung, kecuali memperoleh izin dari moderator atau panitia PKKM. Keenam, peserta yang mengalami kendala selama kegiatan berlangsung dapat menghubungi panitia melalui private chat. Ketujuh, peserta diharapkan berpakaian dan berperilaku sopan selama sesi workshop. Kedelapan, peserta dapat menyampaikan pertanyaan melalui kolom chat atau secara langsung melalui mikrofon setelah dipersilakan oleh moderator. 9, dimohon bagi para peserta untuk dapat mengisi presensi kehadiran melalui tautan yang akan disediakan ketika sesi berlangsung. Dan terakhir, informasi seri selanjutnya workshop PKKM dapat dilihat pada akun Instagram kami, yakni @tpb.ugm, serta akun Facebook atau Twitter di @tpbugm. Diharapkan seluruh peserta mematuhi tata tertib yang ada supaya kuliah tamu dapat berjalan dengan lancar. In this afternoon, we will discuss together with Professor Dr. Dolores Peréz-Marín from Faculty of Agriculture and Forestry Engineering, University of Cordoba, Spain, with the topic Near Infrared Spectroscopy, Principle and Application in Agri-Food Products. We will start this discussion with our moderator. She is Dr. Rudiati Masithoh, STP M.Dev, that will be introduced from this curriculum vitae. Oke, Ibu Rudiati Masithoh telah menempuh pendidikan sarjananya di Teknik Pertanian Universitas Gadjah Mada, kemudian Master of Development Technologies, University of Melbourne, Australia, dan pendidikan doktor di Ilmu Teknik Pertanian, Universitas Gadjah Mada. Kemudian terdapat research interest, yaitu pada tahun 2019 at the National Food Research Institute, National Agriculture and Food Research Organization, Tsukuba, Jepang, dan di tahun 2019 at the Non-Destructive Biosensing Laboratory, Department of Biosystem Machinery Engineering, Chungnam National University, South Korea. Dan kemudian terdapat research interest, yaitu Spectroscopy Methods for Non-Destructive Agri-Food Evaluation, and Machine Vision and Imaging Analysis for Food Evaluation. So, without delaying time, let's start the discussion this afternoon with Miss Effie.
Okay, thank you very much, Hafiz. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome you all to the guest lecture held as the part of the program Kompetisi Kampus Merdeka, which is the independent campus competition program mandated by the Ministry of Research, Technology, and Higher Education of Indonesia. My name is Rudiati Masithoh. I'm a lecturer of the Department of Agriculture and Biosystems Engineering, and I will be a moderator for today's lecture. In this occasion, we will have outstanding presentation from the prominent presenter who I believe shall enrich our insight and knowledge regarding the latest research in findings in the non-destructive technologies in agriculture. Ladies and gentlemen, as we know, food quality is a critical issue, and usually the determination of quality parameters are carried out by conventional chemical analysis, which requires intense work, skilled labors, and also relatively expensive analytical instruments. Therefore, the conventional method is difficult to use with large samples and also for routine analysis. NIR, or near infrared spectroscopy, which cover electromagnetic radiation at 1000 to 2500 nanometers, becomes popular for qualitative and quantitative food analysis. To obtain in-depth understanding about rapid and non-invasive food quality evaluation, we are honored to invite one of our colleagues who is going to present the topic of near infrared spectroscopy, principles and application in agri-food products. Before the presentation, allow me to introduce our guest. Our guest is Dr. Dolores Peréz-Marín. She is a full-time professor at the Department of Animal Production, Faculty of Agricultural and Forestry Engineering, University of Cordoba, Spain. Professor Dolores Peréz-Marín finished her degrees from University of Cordoba, Spain. Her research interests are NIR sensor, spectral data processing using multivariate analysis, food integrity, integration and combination of spectral non-destructive sensor, IoT technologies, and others. Yeah. She is now a new president of the International Council of Near Infrared Spectroscopy. Congratulations, Prof. Lola. She publishes articles of 119 with total number of publication in the first quartile or Q1 of 72 and total number of citation of 2,195 with each index of 28. Yeah, she is currently editor of the Journal of NIRS, FAO consultant and member of the International Scientific Advisory Board of the Institute for Global Food Security, Queen's University, UK. She also awarded in 2014 with the International Thomas Hirschfeld Award and in 2020 with the International G. Birth Award for her outstanding contribution in the field of NIR spectroscopy. And also she is currently the chair of the Cost Action European Network for Assuring Food Integrity using non-destructive spectral sensors that joins more than 30 countries and 200 researchers from Europe and beyond. She's very respected and very experienced researcher. So without further ado, I would like to welcome Professor Dolores Peréz-Marín. She will deliver a presentation entitled Near Infrared Spectroscopy, Principle and Application in Agri-Food Products. If you have any question, you can write down in the chat box or later talk directly to Professor Lola in the end of her presentation. Let me greet our guest. Good morning, Prof. Lola. How are you?
Good morning, everyone. Thank you, Evie, for your presentation. I'm very happy to be with all of you today. It's a pleasure to share this time with all of you and to share some of my knowledge about NIR. If you want, I'm going to share my screen with the presentation and we are going to start with it.
Yeah, you can start now.
I'm going to share. You can see now the presentation?
Yes.
Yes, no? Okay. I have to say that I'm very happy to be here, to can spread the information about NIR spectroscopy. That is my main expertise and is one of my passions. Now that I'm the president-elect of the ICE International Council of NIR, is just not just the passion, is a responsibility to spread this technology around the world. So in this presentation, what I'm going to share with you is, because we don't have time to see everything, but I would like to show you some fundamental of this technology, something about instrumentation and the analysis mode that you can use. Then we are going to go with some spectral data processing and modeling, the main tips. And finally, I would like to show you some applications on agri-food products. Going with the concepts, you know that the NIR means near infrared spectroscopy. It's a vibrational spectroscopy technique. It's based in the absorption produced when the radiation from the near infrared region vibrates at the same frequency of the molecular bonds of the products that we are analyzing. We have to see that this molecular vibration in the NIR region are related to X-H bonds, being in this case the X, carbon, oxygen, or nitrogen atoms. So we have a lot of information in the NIR region. You can see here the electromagnetic spectrum, and you can see that the NIR region that I'm pointing with my mouse, the NIR region is between the visible and the mid-infrared region. This region was discovered by Herschel in 1800, in the year 1800. The region is start around 750 nanometers and finish around 25 nanometers. So this is the region in which we are going to concentrate or to focus today our lecture. As you have seen previously, this is the region between the mid-infrared and the visible. What we have in the mid-infrared, we have the fundamental vibration of these moleculars. And then in the near-infrared region, what we have is the first, the second, and the third overtone of this fundamental vibration. I want to say that these overtones are as an echoes of the fundamental vibration that we have in the mid-infrared. And also we have another thing that is called a combination bands, that is combination of some different energy levels. Because of that, we have less intensity of this information in the near infrared region. We have less intensity than in the mid infrared region, but this has also some advantage. You can see here the absorption bands in the near infrared region. If you can see, we go from the third overtone to the first overtone and the combination bands from around 700 nanometers to around 2000 nanometers. So at the beginning of the near infrared region, we have the third overtone. In the middle, we have the second and the first overtone. And at the end, when we have a higher wavelengths, we have the combination bands. And in this part, we will have the mid infrared. And you can see that we have absorption of different groups at different overtones, but but we have some information overlap. I mean with this that, for example, we can see water at different part of the spectra. You can see here, we can see CH bonds at different part of the spectra. So we have a lot of information, but sometimes this information is overlapped around the near infrared region. You can see better here in this table, in which I put some of the main wavelength that we that are related with the main components in the food products and the main bonds. And you can see here that for seawater, you can see in this wavelength, in this 900 wavelength, also around 4000s and around 1900 nanometers. The same with carbohydrates, the same with fats, the same with protein. So which is the good thing is that we have a lot of information, and this information could be managed with chemometrics to extract and to predict what we want in the sample. The bad thing is that we have some overlapping, and because of that, we need to use chemometrics. This is another example. Now we are seeing here a spectrum. This is what we measure when we take a sample and we take the spectra. This is the spectrum that we obtain. In this case, it's a biscuit. You can see the second overtone related to CH, the first overtone related to water, the combination bands in this spectrum. This is just an example to show you which is the information that we get from an NIR instrument. Also, to understand NIR, it's very, very important to know which are the different interaction that we had between the radiation and the particles of the sample. In this case, if we have a solid sample that is represented here by these particles in green, of course, we can have many different ways of interaction. We can have reflectant, specular reflectant, we can have diffuse reflectant, we can have absorption, we can have transmittant, refraction, and scatter radiation. What we measure when we analyze a sample on NIR is the diffuse reflectance. That means that the radiation arrives to the sample, penetrates a bit in the sample, take information about the sample, and then the radiation is reflected back to the detector, that is to the detector in the instrument. This is the information we measure when we analyze the sample. Sometimes the detector is placed in the other side of the sample, and we have here the radiation and here the detector. We are measuring the transmittance. The radiation that goes through the sample, take information about the particles, and go back and go to the detector in the other side. But also, of course, we can have absorption of this information. We can have refraction phenomena. We can have specular reflectance. In this case, is the radiation that arrives to the surface of the sample and is reflected back. And in this case, we don't have information about the sample. It's like a mirror, and we don't want to have this kind of reflectance, or we can to minimize this kind of reflectance. And also very important at this part of the slide, you can the scatter radiation. Is the dispersed light, is the light that go into the sample and is lost. It depends of the heterogeneity, the side of the sample. It's a radiation that is lost, but it's a phenomena that is very usual on NIR, and it's important to manage all the information. Another important thing is that you must know is that when we work with NIR, we usually assume that the absorption follow the Beer-Lambert law. That means that the absorption values are linearly related to the concentration of the sample we are measuring. So you can see here the absorption related with the intensity of the incident radiation and of the transmitted or reflective radiation. And you can see here that also we can relate the absorption with the concentration and with the path length. The path length is very, very important when we work with an spectral technology as this. When we transmit with the detector is in the opposite part of the sample, the length of the optical path is kept constant by the design of the cuvette where we analyze the sample. But this is useful just for the liquids or for some solids that are not very compact. When we work in diffuse reflectance, that is the most usual analysis mode when we work with NIR, the optical path depends on the microscopic structure of the analyzed material. And in this case, we call about effective optical path. And it's very, very important, the packaging, the pressure that we made in this packaging, because no radiation must reach to the bottom of the cup where we are analyzing the sample. In line with the information that I showed to you before, you can see here the main analysis modes that we use when we work with NIR. The transmission or transmittance, we call transmission when we analyze liquids, and we call transmittant when we analyze a solid sample. And you can see here a sample, the light arrive by this side, and in the other side of the sample we have the detectors. This is transmission because the light go through the sample and is collected by the detectors in the other side. The other analysis mode is reflection or reflectance. In this case, this mode is used just for solid sample. You can see that the light arrives to the sample and the detectors are in the same part of the light, of the incident light. So the light arrives to the radiation, arrives to the sample, and then is reflected back to the detector. You can see here that we have in gray like a surface that is opaque to the light. This is very important because if not, the light could escape from the sample and could not arrive to the detectors. Down you can see what we call transflectance analysis mode. In this case, it's a mixture between transmission and reflection. What we have here is in yellow we have a reflectance surface behind the sample. So the light arrives to the sample, go through the sample, and arrive to this surface, and is reflected again. So go again through the sample and go back to the detectors. When is useful this analysis mode? Is useful when we are analyzing a liquid sample and we don't want to use transmission. In this case, we want to use reflection or reflectance. And in this case, if we use reflectance, as can you see here, the light is in a liquid, the light cannot be recovered usually in reflectance. And at least you use this kind of cuts with this reflectant surface. This is a design that was made to can use reflectance detectors for the analysis of liquids. And the last analysis mode I want to show you is this interactance reflectance. In this case, we are talking about fiber optics probes. We have the sample. Usually we use contact to analyze the sample is contact. We have different rings, and in some of the rings we have the incident light, and in the inner ring we have the detector. So the information travel through the fiber optics to the instrument. So this is very useful for, in particular, for products that have different geometry and are analyzed without any previous preparation. Some general consideration about NIR instrumentation. I want to say that there are now more than 100 NIR instrument manufacturers. So we have a lot of option to decide. We can find in the market instrument, what we call benchtop instrument for at-line or for lab measurements, but also we can find portable instrument or online instrument that allow us to implement or to take the measure on site. And this is very, very important in the advance of this technology for the implementation in the industry. Also, we have predispersive, we have post-dispersive instrumentation. It depends. At the beginning of the instrumentation was post-dispersive, and now most of them are predispersive. We have instrument with one single detector. We have instrument with multiple detectors. We have monochromator. We have diode array, Fourier transform, NIR instrumentation. We have what we have is many different technology for make possible the NIR analysis, and depend on the analysis that we want to do, we can choose one or another. Also, we have difference in the speed of analysis from minutes to milliseconds or even microseconds. We have instruments that work with different range. I mean with this that some of them cover the full NIR region, but others cover just a part of this NIR region with different resolution, different stability. So because of that, the decision for the purchase of an instrument is not easy. It's important to be verified by expert, because if not, it could be sometimes people with not enough information about NIR could make a mistake in the purchase of an instrument, and this is not good for them, but also it's not good for the technology, because we can say the technology is not useful. No, it's not useful for this, the instrument or the decision that you have taken. About the evolution of an NIR instrument, you can see here, I would like to show you these three phases that for me are important. The starting point was in the late 60s to early 80s in the last century, where when we have filter-based instrument. I mean with this that we have instrument just with some specific wavelengths, so they can analyze, for example, 3 wavelengths or 5 wavelengths of 10 wavelengths, but just specific wavelengths. In the second phase, from the 80s to the early 90s, it was very important, the development of the monochromators, that was instruments that cover the full spectrum. I mean with this that we can cover all the region or part of the region, but if we analyze, for example, from 1100 to 2500 nanometer, we cover this region at all. For example, we take its measurement, it's 2 nanometer, of its 5 nanometers. So we call these instruments full spectrum instruments. And now we are in the phase 3, where new technologies has been implemented in the design of NIR instruments. And we have here the delta rate, we have Fourier transform technologies, we have acoustic technologies, linear filters variable. We have a lot of new technologies that enable us to have portable instruments, online instruments that was not possible to have in the past. In picture, you can see here the evolution of an IR instrument. For me, in the last year, is most a revolution than an evolution. You have here Professor Carl Norris. This is the father of our technology, and this is the first instrument, the first NIR instrument in the history. And now you can see how the instruments are changing. And this is what we have here is the new trends in instrumentation. You can see here that we go to instrument, more robust instruments, portable instrument, small sizes of the instruments. You can see here an instrument for an online analysis. You can see here portable instrument, and also pocket instrument, that this is a very, very small instrument. And this is the trends, this is the future of this technology. When we analyze a sample, this is what we have. We have spectra. You can see here several spectra of samples of different agri-food products. I want to say that the NIR spectrum is a fingerprint of the product. We have a unique absorption profile for each sample that we are analyzing, and this is very important for what we call the digital certification of the products. What you see in the picture in this plot is hundreds and thousands of absorbance values. This is the plot, and this is the information that we have when we analyze a sample. This is the information behind the plot. You can see here one sample. You can see here in this line different wavelength. It's 2 nanometers, and you can see here that for each sample we have an absorbance and its wavelength. So we have a lot of information when we analyze a sample using NIR. You can see here another example of a spectra of different agri-food products. For example, in orange, you can see in orange this spectra with 2 bands, strong bands around the area where water is predominant. So in this case, we are talking about milk. Milk is mainly made of water, and is what we see in the spectra. Also, we can see in red and in blue this sample with these bands, these peaks, that are related to samples that have fats in the composition. So of course we can see some different some tips in the spectra, but the interpretation of the spectra, of the NIR spectra, is not easy because as I showed to you before, we are measuring the first, second, and third overtone of the fundamental vibration in the mid-infrared. And this make complex the interpretation of the spectra. So we can see something, but we cannot manage the interpretation as in other spectroscopy techniques. So we need chemometrics to resolve this overlapping and to take the information that we want to have. Adapting to the calibration concepts, when we analyze NIR in an instrument, usually what we measure is, as you can see here in the slide, is the log of the inverse of the reflectance. Usually we don't measure the absorbance, we measure the log of the inverse of the reflectance. We can use this technology for quantitative and also for qualitative analysis of the sample that we are analyzing. For both, we need to develop prediction model, we need to develop calibration or qualitative models using what we call chemometrics methods. With this, what we do is to relate the spectral information with the information provided by a reference method. Just very, very fast, what is chemometrics? Because I'm speaking about chemometrics and sometimes maybe you say, what is chemometrics? Okay, chemometrics is how to get the chemical relevant information from the measurement, from the measured spectral data using mathematical models, mathematical algorithms. So we use the mathematical to extract relevant information from the spectral data. For the development of this calibration or this prediction model, we can use linear and nonlinear regression methods. Usually, I always recommend to apply what is more simple, that is the linear, and in the case we need to modelize something that is more complex, we can go to nonlinear algorithms. Now I'm going to show you, this is a slide that I like a lot because this is the idea of how to develop an NIR application, what we need, and then we are going to see everything in detail, but this is the idea of how to develop a calibration. So what we need to develop a calibration, we need to have calibration samples, a group of samples that we analyze using NIR, but also for this sample, we need to have reference data. For example, we can have information about quantitative attributes. For example, the fatty acid composition, the acidity, the protein content, the sugar content, the moisture content. Or we can have also qualitative information, for example, the type of feeding of a meat in an animal, the variety of a crop, the geographical origin, whatever. So always for the sample that we want to analyze, that could be a meat sample, could be a cheese, could be an oil, could be a fruit. For all this sample, we need to have the information provided by NIR and some reference data. With this information, with this information, with the reference data and the spectral data, we can build what we call a calibration or a prediction model. And you can see here in orange the typical formula of a calibration model. That is, what we want to predict is related to some other variables. in this case, to the variables that we can measure on NIR. So what we want to measure, that is, for example, the concentration in protein is related, for example, with several absorption at the different part of the NIR region. Well, when we have this model developed and we have evaluated this model and we know that the model is robust and the model provides us a good prediction, and we have new sample, we have here in the other side of the slide, new and no sample of the material that we are analyzing. We just need to take the spectra in the NIR instrument, apply the model that we have developed previously, and in a few seconds, minutes, microseconds, it depends on the instrument that we are using, we have all the information about this sample. We have all the information about this sample. We have all the information of the model we have been developed. I mean, with this, if we have been developed model, for example, for predicting 10 parameters, we are going to have in the screen all this information for this sample, and we just need to take one spectra. I mean with this that with one spectra we can have multiple information about the sample. So we can have all the information about composition, all the information about the origin, about just with one spectra. So this is the advantage of NIR. Which are the critical aspects in the development of an NIR application? In my opinion, one of them is the selection of the calibration group. This is very important because the calibration group is the group of sample that we use to train the model. So we train the model with sample that we say, this is, for example, this is red, this is yellow, this is blue, and we train the model with this. We don't use the good sample to train the model, we are not going to have good results. The second important thing is, of course, the quality of the reference data, because as you know, we need some reference data to develop the models. So we need good reference data to develop the models. Of course, the spectral data quality is also important. And finally, also the development and evaluation of chemometrics models. I mean, with this, the spectral pretreatment used, the regression methods apply. And you can see here in this formula that all of them are related. So if we have here the error of the model, the total error of the model, of my NIR model, this total error is influenced by the error of the lab. So the quality of the reference data is important. It's influenced by the error of the NIR method. So the quality of the spectral data is very important. And it's also influenced by the error of the model, how I fit the model. So in this case, the chemometrics model is important. But I want to say here, I want to make to highlight here that for me, the two most important aspects are the quality of the reference data and the spectral data quality. Why? Because the others can be changed if we have, for example, if we develop a model and we have not a good adjustment of the data, we can repeat the model as many times as we want in a very few time. But if we have bad reference data, or if we have bad spectral data quality, sometimes this have not solution in the future, because sometimes we don't have the sample to repeat the measurement. Sometimes we don't have the instrument in the same situation. So it's very, very important to take care of have good quality in reference and spectral data. And then the other, of course, are important, but if we have a mistake in the other part, we can solve this mistake in a easy way that if we have a mistake in the other part of these critical aspects. I'm going to go through very fast to some of them. So for the selection of the calibration and training set, it's very important that you identify the variation sources in the product to be analyzed. I mean, we did that for developer calibration, we need variability. We need several samples, but we need variability in the sample. If not, we cannot develop the calibration. And for this, it's important to know which are these sources of variance. So for example, if you are analyzing a cereal or a crop, it's important the variety, it's important the climatic factors, it's important the soil type, the irrigation practice, the fertilization practice. All these things are going to influence the result of the product that we are going to have. In addition, if we are talking about a processed product, for example, an oil, or for example, a biscuit, or for example, mixture of things, we have to take into account these factors, but also the ingredients, the process condition, temperature, pressure, time. All these we have to take into account to recover or to cover the variability that we want that we have in our population. Then when we know these sources of variance, we need to accumulate a group of representative samples that cover this variability, including chemical, physical, and spectral composition. Which number? This is always the question. Which number? How many samples I have to analyze? Okay, I have not the answer. I have some tips. So usually when we work with agri-food products with NIR, we need more than 100 samples to have a robust model. With less than 100, the calibration usually is very unstable. If we have a very homogeneous product, we need less sample to cover the variability. If we have a very, very heterogeneous product, we need to increase the number of the calibration set to cover this variability. But more than 100, and usually 100 or 1,000 of samples, it depends on the application. And it's very important to select properly the calibration set, because this calibration set is going to determine the stability and the accuracy of the models. For doing this selection, this sample selection, we have available some tools that allow us to see the population structure and to select samples. And for this, the most important is the use of principal component analysis. In this case, we reduce the data collinearity. We have a lot of, as I say previously, we have a lot of overlapping in the data. We have some collinearity in the spectral data, and it's good to reduce this collinearity using some tools as the principal component analysis. And then once we have the spectra in components analysis, in principal component analysis, we can calculate the spectral distance. And in this case, in NIR, one of the statistics more used is the Mahalanobis distance, the age. This is a very, very useful statistic. How this kind of tools works? Well, for the reduction of the collinearity, as I mentioned before, we use principal component analysis. We can use also PLS, partial least square analysis. With both, what we do is an orthogonal transformation. The difference between PCA and PLS is that PCA is just based on spectral information, and PLS take into account spectral and also reference data information. What we do when we apply principal component analysis is to reduce the number of variables, and to calculate a new axis. For example, if we are working with an instrument that measure the spectra in the region 1100 to 2500 every 2 nanometers, what we have is that if we make the difference between the end and the beginning, we have 1400 nanometers, and as we take the nanometer each 2, we divide it this by 2, and we have that we recover until 700 data points with this instrument. So we have 700 variables, we have 700 axes. So this is a very, very complex population. And also, as I mentioned before, we have information that is redundant along these variables. So because of that, we apply a principal component analysis to reduce this collinearity and to reduce the number of axes in which we are expressing our population. So we reduce the number of axes to a linear combination. We are going to have less number of axes, but these axes, the unused axes that are called principal component, and linear combination of the all variables. This means that, as you can see here in the slide, that the principal component 1 is a combination of the previous variables. That was the other variables were the wavelengths, and the same for the second principal component, the third. So how we compute the principal component? The first one explains the largest variance in the data. The second is calculated in the same way, but must be uncorrelated with the first, so must be orthogonal to the first. And in this way, we continue until we calculate NPCs. When we have these new orthogonal axes, we don't have collinearity in the data. We have the information, we have all information, but we have reduced the dimensionality, and we have the information uncorrelated. So this is good. This is an example that I showed to you before. This is an spectral file with information. Here you have wavelength, and here you have the sample, and for each sample that you have here, you have the absorbance at each wavelength. When we apply principal component, we have what we have there. That is, you have here the sample, and in the first row, now we don't have a wavelength, we have principal components, the first, the second, the third, the fourth, and we have now for each sample other scores. Other score in the new axis. So this is what we have do, just to change the axis to do them uncorrelated, and this is good. For the structuring of the population and the sample selection based on this principal component analysis and the calculation of spectral distances, you can use these two algorithms that are described in the scientific literature. You can see here the references, and it's the center. They are the center and the select algorithms. The center algorithms allow us to identify sample with spectra very, very different from the population center. So in this case, if a sample is very far from the center, it means that it's very different, or it means that it's from another product. and the select detect sample with sample that have a very similar spectrum. And in this case, select that sample that has the biggest variability in the population. So in this case, this select allow us to select the population with more variability. You can see here just step by step that both algorithms, the center and the select, make first a PCA analysis. As you can see here, we can change from wavelength to PCs, and then we can they measure the Mahalanobis distance, the age statistic. In this case, in the center, they measure the distance from each sample to the center of the population to detect if we have some outlier in the population. And with the select, we measure the distance between sample, and then we select the representative of each class. So with this, we are going to have the sample with the biggest variability in the population. Going now with the quality of the reference data, that is also the second factor, critical aspect for a calibration development. I must say that any measurement that we take has an error. Usually we think that just NIR has error, but not. Any analytical or any measurement that we take has an error, and the error is the difference between the measure and the true values. How we improve the estimate? To improve the estimate, we take several measurements, and then we use the average of these measurements. We can calculate when we use when we develop the methodology for analyze the reference data. We can calculate the standard error of the laboratory. This is the error of the reference data. It's important that this error is calculated for each type of product and for each type of constituent, because the magnitude of the errors is always related to the parameter, to the value of the parameter that we are measuring. So, for example, if we are measuring protein in meat, is not this. We are not going to have the same error. That is, we are measuring protein in wheat. It's not the same. And also it's recommended to take duplicates, but that the duplicates must be, this duplicate must be blind. I mean with this that the analyst should not know that we are evaluating the method, because if not, the results are not very, very real. And just to show you, you have here the equation for the calculation of the standard error of laboratory with a different number of replicates. And if we have two replicates, if we have duplicates, in this case, the equation is less complex. You can see here that we have in the top the difference between the two values. This difference is square, and the summatory of all this difference is divided by twice the number of sample. We take the root square of this ratio. You can calculate this in Excel using the formula. I recommend you to do this, because this is the comparison. Is need to compare the standard error of laboratory with the standard error of our model. And here I want to show you the importance of the quality of the reference data with an example. Here, what we have is a calibration for the prediction of the composition in molasses. You know that molasses is a pasty product. In this case, we analyze moisture, protein, ages, salt, and sugars. And you can see here that this is the error of the model, and this is the R-square of the model. And what we want to have is a very small error and R-square close to 1. And you can see here that for all the parameters, we have very good results for protein, ages, salt, sugar, but not for moisture. And I have to say that moisture water is very well seen in the NIR region. So we have a very strong absorption of water in the NIR region. So why we have this bad result in this case in moisture? Well, the answer is that in this case, we analyze the reference data were provided by the industry with a very fast reference method. Is a infrared balance that is not very precise. So we have very bad result with a not very precise reference data method. But we decide to analyze the same samples with the with the official reference method to analyze moisture in pasty products, that is in the oven, and the methodology recommended by the official inspection. And then you can see here that the error was reduced a lot from 1.69 to 0.34, and the R-square was increased more than the double. So what means this? This means that in this case, we can prove that the quality of the reference data, it's very, very important to have good results. And you can see here with an example. Now, we are going to advance to the quality of the spectral data in this case. Of course, NIR is very easy to use. It's very easy to take a spectra with the instrument, but of course, we have some error sources that is good to know in order to minimize, or at least to know that we have these error sources on our data. One of these is related to the instruments. Of course, not all the instruments have the same signal to noise ratio, and not all the instruments have the same wavelength accuracy. So, of course, there are instruments with better technical quality and other with not so good technical quality. For example, if you compare, usually the portable instruments has less accuracy than the instrument used in the lab. So, okay, we have some information that is lost because the quality of the signal. Of course, another error sources in this case is the one related to the sample. It's not the same to analyze a sample with a very homogeneous sample or a very heterogeneous sample. Is influence the temperature, the density, the texture. So this is also important. You can imagine that it's not the same, for example, to analyze a tomato than to analyze, for example, a grain of wheat. Usually to analyze wheat is easier than to analyze a tomato. So this is the comparison that you have to think. And also we have some operational, we could have operational problems, sample preparation if we need, not with the new instrumentation. Most of the time we don't need sample preparation. We can have analysis errors. I have to say that it's very easy to use this technology, but of course, if we are not, if we don't follow a methodology, we can make some mistake in the analysis. And also it's very, very important the optimization of the mode of analysis depending on the product type. If we are analyzing a solid, we are analyzing a positive product, we are analyzing a liquid. For example, I have to say that usually a liquid could be more challenging than a solid, or it depends on the solid, but could be. We can decide if we have to decide if we use reflectance, transmission, interactance, if we are going to take the measurement in the lab or to take the measurement online, on farm. All these decisions affecting the quality of the spectra. I have to say that one of the main problem is that we are using the non-correct mode for analyze. So for example, if we use the reflectance, we can just analyze liquids. We analyze, for example, a folded transmission cap. So these things we have to take into account to record a spectra of quality to can work with this. Of course, you can use some statistics to evaluate the quality of the spectra. This is one of them, the room mean square. The room mean square calculates the similarity between two spectra of two subsamples. The calculation is made point by point. We can also establish a cutoff limit for the type of sample or for the type of product in order to know if we are doing a good analysis or not. And the last one, but it's not the less important, but it's the less important in the sequencing, is the development and evaluation of chemometrics model. We are going to see the importance of different spectral pretreatment, regression methods. First, I would like to say you why Nir technology needs chemometrics methods. I have commented before, but I'm going to highlight, to stress here that first reason is because the spectrum contains a large amount of information, and part of this information is redundant, so we have collinearity in the data. As I mentioned before, we can see water in different part of the spectra. We can see fat in different part of the spectra. So the information is repeated along the spectra. And the other reason is because the spectral variability is not only due to chemical differences. In the spectra, we have also influence of moisture, of the temperature, of the particle size, of different physical parameters. That is good because we can measure physical parameters using NIR, but sometimes can interfere in the measurement of chemical parameters. So because of that, we need to use chemometrics, and we used to use multivariate analysis. This is an example to show you how the differences in particle size affect the spectra. You can see here in the plot the same sample analyzed at different particle size, and you can see that we have difference in the absorbance of the spectra. This is also consequent of an effect that I mentioned to you when I show the interaction between the radiation and the material, that is the scatter effect, or also called the dispersed light. And this is consequent of the optical heterogeneity of the sample. And if we have sample with different shape, different size, this effect is bigger than in sample that, for example, we have very with a very fine milling, or for example, we have less scatter effect in a liquids, in an homogeneous liquids. So it's because we have differences in the refractive index, and we can see in the spectra different effects. additive, multiplicative, and also variation in the pathline. You can see here in this plot the original spectra in yellow the same spectra with an additive effect, that is we have more absorbance, but also we can have multiplicative effect that you can see that we have the differences are bigger when we advance in the wavelengths. So at the end of the spectra, we have more difference. This is typical of the scatter effect, but also we can have a baseline curvature in this spectra. When we have an NIR spectra, the spectrum is not parallel to the x-axis as in other technologies. Instead of this spectra is going up along the wavelength range. So to eliminate this effect affecting the spectra and to make the signal clear, we use different spectral data pre-treatment as the smoothing, the derivatives, maybe you know the Savinsky-Golay derivatives or the Norris derivatives, and also some scatter correction methods as the multiplicative scatter correction, standard normal variate, the trending, or the combination, or several of them. So usually we pre-treat the spectra to make the information that we want to make more clear, to enhance the signal. Here you are some example in the plot on the top. You have the same sample analyzed at different particle size. In green and blue, you have the sample analyzed without milling. In the yellow and orange line, you have the same sample analyzed in different cups, but in a ground way. And you can see difference in absorbance, but when we apply some pretreatment, you can see in the bottom this plot, we applied some scatter correction and some the first derivative. We can see that the difference are reduced, and thus we can see in a specific part of the spectra some differences that are related maybe to the chemical composition of the sample. Another example, you have here some raw spectra of a cereal. You can see here that even the spectra are very similar, but we can see a long variation in absorbance in this population. And when we apply a scatter correction, second derivatives, this is the spectra that we have. We have more, you see that we have more peaks, but the important thing is that the main differences are concentrated in specific peaks around the spectra, not in all the spectra. So this is good to can extract the relevant information that we have in this spectra. And now going to the development of NIR prediction models, just some information very, very fast. As I mentioned before, we can develop quantitative analysis. We call in this case calibration. What we do is to develop multivariate models, could be linear or could be non-linear, for the quantification of the parameter of interest. For example, for the prediction of the acidity in an oil, for the prediction of sugar content in fruits, for the prediction of protein content in meats. And in this case, as methods, we use, for example, multiple linear regression. We can use PLS regression, or we can use more complex tools, as for example, artificial neural networks or local regression. Both are nonlinear adjustment methods. Also, we can develop qualitative analysis. In this case, we develop discriminant models to separate the population in classes or to authenticate sample. I mean with this that, for example, we can separate olive oils in commercial categories. We can discriminate, for example, between sweet and bitter almond. We can authenticate rice origin or variety. So we can do many things in this quality approach. And in this case, the method that we use are different. We use PLS discriminant, we can use Syncal, we can use cluster, we can use different methodologies. Just to let you know, when we develop a calibration, just very fast to let you know the difference between the use of different linear methods and to introduce PLS, that is one of the methods more used in NIR. In the past, most of the calibration were developed using M.Dev, multiple linear regression, and in this case, what you have here is this: you have that the attribute that you want to measure, for example, the percentage of moisture, is related to the different variables that I analyzed in the NIR. So this is wavelength. These X here are wavelengths. So as in the past, the instruments measure just a specific wavelength, we can use this to relate information that we want to analyze with this specific wavelength. But when the development of the full spectrum instrument, we have developed also the full spectrum regression methods. And in this case, we speak about principal component regression or partial least square regression. Similar to what I explained when I explained about principal component analysis, in this case, it's not analysis, it's regression. We are related spectral and reference information to develop a model. In this case, when we use PCR, we use just the spectral information to calculate the term of the equation. And in this case, we use the spectral and the reference data. This is the most used method when we use NIR. What we have here is that in this case, the equation is the same. We have that the percentage of the attribute that we want to measure, for example, the moisture, is related to the information provided by the instrument. But in this case, each PLS is not just one wavelength, it's a combination, a linear combination of the different wavelengths analyzed in the instrument. So this is the difference. So this is a more complex model than the MLR model. To illustrate this, you have here this example. For example, to analyze in this case the moisture in a cereal, you can see here that I have this this model just with one variable, and is that the moisture is this coefficient plus this coefficient by the wavelength, by the absorbance at this wavelength. So this is the model. And with this model, I have an error of 1 and an error square of 0.4. Okay. If I use another variable more, is I use multiple linear regression. In this case, this is the model, this coefficient plus this coefficient by the absorbance at this wavelength, minus this coefficient plus, by the absorbance at this other wavelength. This is the model. We have in this case two terms in the models, and in this case we reduce we have reduced the error of the model from 1 to 0.3. We have increased the R² until 0.9. Okay, so it's better. The adjustment in this case is better than the adjustment that I did with just wavelength. But I can do also PLS, and in this case, I cannot write the model because it's more complicated. But what I have is that with the software recommend me to a model with 7 terms and with this error and this R². So I have increased the precision and accuracy of this model with PLS. So in this case, you can think, okay, I have the clue. If I added more terms, I'm going to have better result. No, we have to add just the right number of terms in the equation, because if we use just a less number of terms, we can be underfitting the model. So in this case, it's not good, but if we add an excess number of terms, we can overfit the model. So because of that, when we use PLS, usually we use PLS with cross-validation to avoid the overfitting and to select the optimum terms, number of terms of the equation. In this case, the calibration set, the sample of the calibration set is divided into several groups of different sizes, and all the samples in the calibration set are used to validate at some time during the calibration process. This is what I mentioned before. When we have, this is the model complexity, is the number of terms of the model, and this is the error. So please see this curve, the blue curve, the dark blue curve, and you can see that the error is reducing when we increase the complexity of the model, but there is a point when the error starts again to rise. So we have to look for this minimum when we make a model, when we fit the model. And what I was explaining before is that in cross-validation, we divided the calibration set in several groups, and during the process, in some way, some of the samples are used for calibration and all the samples are used for validation. So we are going to have an error of this, that is the best estimation of the best estimator of what is going to happen with my model when I use the model to predict new sample, because with the cross-validation error, I'm going to I'm estimating how the model is work when we analyze new sample. So it's a very good option for evaluate the model. Going now with the statistics used for the evaluation of the models, we have the R², that is the determination, the coefficient, the determination coefficient, sorry, and it's mean that is the percentage of explained variance of the model. This means that if we have 0.7 of R², the model explains the 70% of the data variability. So because of that, because we want to explain all the variability, we want to have an R² close to 1. And then the most important is the estimation of the uncertainty of the model. And we can estimate this with the different statistics. We have the standard error of calibration, but in this case, this is not good because just show us how the reference and the spectral data are fitting, but it's not show us how, it doesn't show us how the model is going to work in the future when we apply the model to new sample. For this, we must use the standard error of cross-validation or the standard error of prediction if we do external validation. And also, if we are doing a qualitative analysis, we use the percentage of sample correctly classified. Some tips to interpret the R square. If we have an R square over 0.9, we have an excellent adjustment. Between 0.7 and 0.89, we have a good adjustment. Between 0.5 and 0.69, we have a good discrimination between three range, height, medium, and low values. Between 0.3 and 0.49, we have the discrimination between two levels, height and low values. Below 0.3 is better than don't analyze, but really we don't have a good adjustment of the data. Going now with the error, with the uncertainty of the models, just to show you that, as I mentioned before, the most important is the standard error of cross-validation or the standard error of prediction when we do an external validation of the model. And you can see here the formula. What we have is that the root mean square of what we have there is the differences between the value or the reference value and the value predicted by the models. And then we have this difference, all the summatory of this difference square with the square elevated and divided by m. You can see here that this is the most important, because what we want when we develop a model is to predict the sample, to predict the values as much close to the true value that for us is the reference data. So with this statistic, we are evaluating this differences, that is the residual. And what's the meaning of this statistic? As I mentioned before, it's the uncertainty of the prediction. Generally, when we use NIR, we consider that that we want to be confident in the results in the 95% of the cases. So because of that, when we say a number, we say that this number is true. For example, if I say 10, is 10 plus minus the error that I have, or plus minus 2 times the errors that I have. So for example, if I say this product have 10 of proteins and I have an error of 0.5, it's 10 plus minus 1. So my confidence interval is 9 to 11. So the true values will be between these values. So because of that, we want to reduce a lot the error in order to have a narrow confidence or interval confidence. You can see here that this is statistical. This is the Gauss distribution, the normal distribution, and you can see here that below we have here the mean value, and from the mean value to 1 time the standard deviation. If we paint in blue, in dark blue, we have the 60%, the 68% of the population. If we go 2 times from the mean, 2 times the standard deviation from the mean, we have the 90% of the population under the curve. And then if we go 3 times from the mean, we have the 99.7% of the population under the curve. Because of that, when we speak about the confidence interval, when we speak about the error of the model, we usually, to be sure in the 90% of the population, we say the value plus minus 2 times the standard error of prediction of the standard error of cross-validation. How we can interpret the set is useful to compare the standard error of prediction with the standard error of the laboratory, because we developed the model with this standard error of prediction of the model very similar to the standard error of laboratory. We have an excellent accuracy. From 2 or 3 times we have a good accuracy, and from when we are far away of this, 4, 5 or more, we have medium or low accuracy. So what we want is to have a standard error of prediction very similar to the standard error of laboratory. Other statistics that could be useful are the RPD, RER, or coefficient of variation. All of them are statistics that allow us to standardize the result. In this case, we standardize the results using the standard deviation of the population, in this case, using the range of the population, and in the case of the coefficient of variation, using the mean value of the population. We cannot compare the data just at error level. So, for example, if I say to you, we have an error of prediction of protein in wheat of 0.3, and in the case of the prediction of protein in soya meal, we have an error of 0.5. Which is the best for you? Which is the best model for you? Usually, most of the people say, for me, the best is this, because had the low the lowest error, but it's not true. What I will say is, I cannot say anything because I have not enough information. So I need more information. For example, I need the mean value of the population. So if I know that the mean value of the population is 12 for wheat and 44 for soya, I can calculate, for example, the coefficient of variation, that is the relation between the error of the model and the mean value. And you can see here that for wheat, we have a coefficient of variation of 2.5, and for soya, we have 1.14. So in this case, it is better. This is better the model for the prediction of protein in soya. So at the beginning, we have problem to decide, but with the calculation of these other statistics, we can standardize and we can compare equation of difference mean, of difference standard deviation. Usually, when we develop a model, then we have to, before to use the model in routing, we have to validate the model with a group of samples that have not been included previously in the development of the model. This is what we call external validation. I'm not going to explain in detail, but we have to use a statistic protocol for this external validation. This is one of the protocol that exists, but at least we need 10 samples for development of validation to have significant results, and we have some control limits. We have some statistic to evaluate if the model is good or not. You can see here that we calculate the standard error of prediction, the bias, the slope, the R-square, a lot of information to decide if the model is working properly or not. And then when we evaluate the model and the model is good, the model is robust, we can use this model in routine analysis. In routine analysis, we just need to collect the spectra of the new sample. We apply the model that we have previously developed, and we have the instantaneous prediction in the screen. And also we have some information about some statistics that are allow us to detect if the prediction is good or not, because now we don't have information about the reference data. We have just the information about the prediction model. So it's good to have some information to help us to take decision. And in this case, we have the GH, the NH, and the T. We are going to explain now. If we have some outliers, if we detect that the prediction is not good for some sample, we have to send this sample to the lab. And if the results confirm what the reference say, we use this sample to recalibrate, because I want to say that this is a dynamic process. The equation, the calibration are dynamic, so we have to recalibrate every year. Of course, when we have a robust calibration, every year we maybe need to add just 10, 15 sample, no more. But it's good to recalibrate with the new variables, with the new variability that we are recovering every year. The outlier detection that I mentioned before are these. We use the T student statistic to detect chemical outlier, and we use the Mahalanobis distance, the GH and the NH, to detect what we call spectral outliers. The outliers are very important, so we have to try to understand them, not to just to remove. You have to understand them, to know why we have this outlier, because this is the way to advance in the improvement in the improvement of the models. Of course, the T statistics, we put the limit in 2.5. So when we have this significant difference between the residual, we have to see if we have bad data, if we have samples that are not representative, if we have extreme values, whatever. And for the spectral outlier, we use the Mahalanobis distance. We use the GH, that is the distance between each sample to the center of the population. And in this case, we see if the sample is quite far of the population. And also we see that the NH, that is the neighbor Mahalanobis distance. And in this case, we measure the distance between the sample to other similar sample in the population. If we don't have many similar samples in the population, it's more difficult to predict this sample in a properly way. And this is an example. We have a routine equation for the prediction of composition of meat. We analyze the meat, and we have the fat content and the moisture content, and also we have the global age, the neighbor age, and the T. All of them are below the recommended values. Global age under 3, neighbor age under 1, and T under 2.5. So these predictions are good and we can use. And now I'm going to go to the last part, to the application in agri-food products using NIR. I'm going to say to you that the trends in food and process control in the agri-food sector is to go to assuring the food integrity, I mean quality, traceability, safety along the whole food chain. I mean with this that we have to cover not just the final product. Instead of this, we just to cover the primary production, the crop, the livestock, the process in the industry, the transport and distribution, and also the final product that arrives to the consumer. To do this, the traditional analytical methods are not enough because they are time consuming, they are very expensive, they are destructive. So we need other option, and in this case, NIR could be one of the option to increase the transparency and to increase the trust of the consumer in the food system. And why NIR is very, very suitable for this? Because NIR is very fast, it's precise, it's easy to use in routine analysis. Of course, development of the application are not easy, but the using routine for every technician is very, very easy. It's very versatile. We can use NIR for many different products and many different attributes that we want to know for each product. It's non-contaminant. We don't use reagent and we don't produce waste. It's low cost. It's non-destructive. So we can analyze all the production because it's a non-invasive technologies. We provide a better inspection because we provide better sampling of the sample, and it could be implemented along the process. And also it's a digital signal, and this provides us many opportunities to use NIR as an Internet of Things devices. What we can measure with NIR? We can measure organic compounds of many products, but also we can measure inorganic components by indirect correlation. As I mentioned before, what we measure are the organic components, but we can measure inorganic components by indirect correlation or because they are associated with organic matrices. For example, we measure H's in all the products, and H's are the minerals, so we can measure also. Which concentration? Also, you can find some studies and some application with go to low concentration. I have said that more or less the limits of this technology, it's around 100 ppm. So it's not the best technology to detect traces. For this, we have other technologies. We can measure physical parameters, we can measure chemical parameters, we can measure other parameters, ingredient composition and sensorial attributes. So we have a lot of possibilities. We have also limitation. The first limitation is that most of the case is used as a secondary method, and calibration is required using a reference method. It is influenced by non-chemical factors as temperature, particle size, and this is good, but this is bad when we want to analyze, in particular, attributes, chemical composition that is in minor minor components of the products. Also, it's very important. It's not an analyzer, so an implementation project is required. I mean with this that you can buy the instrument, but the instrument without the application is nothing. So this is sometimes the main limitation of NIR, because sometimes when we work with the industry want to have the answer for today or for yesterday, and sometimes this is not possible because we have to develop the application. To recover all the variability in a product is not always easy. Which are the main potential application of? We have application in all the fields. We have application in agriculture, in food, in ecology, in environment, in chemical, in pharma, in biomedical. Biomedical is developing a lot in the last few years to measure chemical composition, physical attributes, qualitative attributes, sensory attributes. So we have a lot of possibilities. I would like to introduce you that the European Medicine Agency has published a guideline on the use of NIR for the pharmaceutical industry, but it's a free document you can download from internet. You can have some tips and guideline for the use of NIR, so I encourage you to download from internet. Also, NIR, you have some official information. For example, this is the international standard for animal feeding stuff, cereals and milk cereal products for the use of near infrared spectrometer. And I'm going to show you very, very fast some of the application we are working on in my group. We work a lot in animal feedings because I'm in the animal production department. In animal feeding, this is one of NIR is a very well-known technology. It's very well implemented in the industry because NIR provides a solution for the analysis of raw materials and for final products, I mean with this, compound feeds, total mix ratio, for provide information about the chemical composition, moisture, protein content, fiber content, starch, but also for the ingredient composition and others. For example, in my thesis, I developed the application for predicting ingredient composition in a compound feeds. This is the different type of compound feeds I show you in order you can see the high heterogeneity that we have in this case with this product with many different ingredients, many different formula. So it's a very heterogeneous product. This is the comparison of the analysis mode. When I started working with NIR, everything was analyzed ground and was analyzed in these small cups. And we started working with the products without a previous milling, what we call intact product. Here you have the comparison between the different modes to predict in compound feeds, moisture, protein, growth, fiber, and ACEs content. And you can see that the standard error of cross-validation is quite similar for all the methods, all the analysis modes, but even sometimes it's better when we analyze the products in intact. So this means that from this time when we demonstrate that we will have the same precision using this analysis mode, from this time we avoid to mill the product before the analysis. And this was the starting point of the actual NIR analysis with portable instrumentation and with offline instrumentation. Also for the development of application for the ingredients composition in a compound feeds, this is part of my PhD thesis. You can see here that in this case, the calibration set is very important. We need large calibration sets. We need a lot of variability. And of course, the chemometrics was very important. And in this case, we have to test nonlinear calibration. In this case, what we are predicting is not composition, is the ingredient, for example, in a mix, the percentage of wheat, the percentage of barley, the percentage of soya. We work with more than 7,000 samples, and this is the validation results that were not very good for many of them. But when we apply a nonlinear method, in this case it's a local regression, I'm not going to go through what is local, but it's a nonlinear approach. You can see here in this column versus this column that the error were reduced a lot, and we have a very good result using, in this case, nonlinear for this complex application. And this is the final application. We have a sample, an intact sample, we take the spectra, and in a few seconds we have all the information about the chemical composition and about the ingredient composition. Then we start to move to the plant, and we decide to analyze the product in the resection in a medium point after the mixing and before the packaging. We start with different pilot assays because at the beginning we didn't know if we can analyze the products moving along a conveyor belt. So this is the first analysis of this, and this is the first implementation in a feed plan, and this is how is now the NIR in this feed plan. So the solution in this case is the adaptation of the instrument to the existing plan. Now the instrumentation have changed a lot, as I mentioned before, and now we have new instrument as the one that you can see in the picture. This instrument is a multiplex instrument with 6 channels. This means that we can measure in 6 points of the plants at the same time. Also, we are working with a portable instrument at the one that you can see in the picture. Another important thing when we work on animal feeding is that we have to analyze large volume of sample. You can see here in the harbor, in the ship, we are talking about tons of products. The same in the truck that arrive to the processing plants. We are developing a project to develop a Prof adapted to an NIR instrument to analyze directly the product in the container of the truck without unloading the product. We have working a lot of design of this Prof. It's not an easy task, but at the end we developed this, that is the best option with several windows along the Prof to analyze the product at different heights. The idea is to develop the robotic arm with the Prof and can analyze in different points of the truck directly and in an automatic way to decide if the product have the quality that we want or not. Also, we have worked a lot with oils. At the beginning, we started with this kind of caps. This is the folded transmission cap. This is a reflectant surface. Allow us to analyze liquids in a reflectance detector instrument, because this reflects absolutely completely the radiation. Also now we use other instruments with, for example, transmission Prof, and also the portable have option for transmission and transflectance to analyze liquids in the way that you can see in the slide. This is the typical spectra of olive oil with a very marked peaks in this and these regions. And for example, we are predicting several parameters of quality like acidity, peroxide index, esters, moisture, impurities with a very good result. Also, we can predict the sensory properties in olive oils. I mean, with this, the fruity, the bitter, and the pungent values, taste values. This is because NIR has information not only about chemical composition, but also other information in the spectrum. Also, it's important the detection of adulteration. You can see here how we can separate very well olive oil from samples of olive oils adulterated with corn oils. That is the adulteration is a very important field for working with NIR. Also, to detect geographical origin is very, very useful for this. In this case, it's for olive oil, but you can use for rice, you can use for tobacco, you can use for other for saffron, for whatever. And also, we have developed a Prof to analyze directly in the tanker trucks the quality in this case of the oils. This is another project. Going to the analysis of raw meat, you can see here different options to analyze the meat with different instruments, portable, online instruments. In this case, one of the application is the discrimination between fresh and between frozen and thawed meat. This is a quality problem because sometimes in the market appear some meat that had been previously frozen, but now is thawed and we don't know. So we can discriminate perfectly both the fresh and the frozen and thawed meat. This is also very important for fish because this is a problem that we have with fish as well. Also, we can predict the meat composition, fat, moisture, protein. Also, we are working now in a very challenging project that is the authentication of the breed purity. In this case, is pork meat. We have some different type of pork meat, and sometimes come from pure bread, and sometimes come from crossbred. And you can see here that we can discriminate the pork breed with a 90% of hits. Also, we have advanced in the in situ analysis in the slide with portable instruments, and also we try to analyze the live animal, the in vivo animals with these instruments, because the NIR is a non-invasive technology. For this, we predict a fatty acid profile. You can see here in vivo, in the carcass, and in the fat directly. Of course, we have better results in the fat, but the results that we have in vivo and in the carcass are very, very good. Also, in the case of the ham, Iberian ham is a very typical product of Spain, and we have several different commercial categories, and we have different prices, of course, and we can discriminate, the classes between the premium, the first class, and the second class quite well, even in validation, with a percentage of hits over 96%. Also, as I mentioned, that we can use NIR as an IoT device, we have developed a digital labeling platform connected to the cloud and connected to an app in the mobile to provide consumer with more information about the products. The idea is that the product have a QR code, and you can read the QR code with the mobile, and you can have the information provided by the NIR in origin through this complete interface or platform developed. Going now to the analysis of fruits and vegetables, I have to say that in this case we have more problem because we are working with high moisture products, and also because we are talking about a very different products with different geometries, different size, are perishable, that this is another drawbacks. And also we have difference between individual pieces, so this make more difficult the analysis. But the portable instruments have provided us many options. You have here one working with nectarines in analyzing them in the trees, to detect the sugar content and the firmness. Also, in this case, is the variety authentication in plants, and we have very good results with the portable and with the benchtop instrument. Now we are working a lot in watermelon, that is a typical product from Spain, and this is a very complex application because the skin that have the watermelon is very thick. It's quite difficult to get a good signal from this, but we have very good results using analyzing the product without cutting the product. So it's very promising, and now we are working with the new instrument that we have in our lab for a company that is interested in implement the technology in the plant and also in the field. Also, you have here the prediction of texture in green asparagus analyzed, as you can see in the slide. Also, this is the discrimination between green asparagus varieties, between an autochthonous variety and a hybrid variety. In this case, what I showed you is the discrimination between organic and conventional products. In this case, we are talking also about asparagus. Also, we are working now in the prediction of nitrate content in zucchini. There is an European legislation that limited the nitrate content in vegetable, in particular when used for baby food, because this product can be toxic, can have some toxicity for human. We have very good results working in zucchini with this kind of instruments. And also the same, we are analyzing spinach with online instruments and also directly in the field. And in this case, this is the instrument of the company that has working and have taken decision with this technology. In this case, this is pepper analysis to discriminate between different growing systems between open air and greenhouse products. This is a quality application of NIR. In the case of almonds, we are using different instruments to evaluate the possibility of discriminate between sweet and bitter almonds. And you can see here that the detection is perfect. We are discriminating between sweet almond and sweet almond adulterated with a small amount of bitter almond, 5%, 10% and 15%. And the discrimination is perfect. And finally, I would like to talk you about what we call non-targeted approaches. That is a way to study the profile of the product using NIR. So I would like to take your mind to bring your mind to the melamine, dioxins, oxyl oils adulteration, horse meat. All of them are food frauds, food crisis, but who will be the next food crisis? I don't know. Maybe you don't know, because now, of course, we control these products or these adulterants, but we don't know which will be the next fraud. So because of that, we need to change how we monitor the food. It is not always necessary to replicate the answer of the reference methods. When we talk about reference methods, we talk about target methods that looked for a specific analyte. When we talk about non-targeted methods, we talk about methods that can detect and identify analytes that shouldn't be there. So NIRS could be used as a non-targeted method and enables us to develop what we call a food fingerprint, a digital certificate of the product. In this case, you can see here that we have to develop a target of the product. This is our target, this is our standard, and we can calculate also the warning and the action limit. And each of these points is an spectra. And when the spectra are below the action limit, it's okay. And when these spectra are over this action limit, wait, take care. We have to look, this is like an alert. We have to say, okay, maybe we have a problem, maybe we have changed something. We have to know which is the problem. And this is, I would like to introduce, because I think this is the way we are going to work in the future, in the process control, in the near future, not in the long future. In the near future, this is the way we are going to innovate our control system, because we are working just with spectral information. Not in this case, NIR is using alone, not as a secondary method. And this is very important. This is very fast. and this allows us to have more information about the products on real time. And just to finalize what is coming for the future, the role of NIR for the massive sampling of wood products is very, very important. We are going to be able to inspect more products. Of course, the integration of several spectral sensors for critical issues in the agri-food sector. For example, the combination with NIR with imaging, we are working with this. And for some application, for some problem that we have, we need to combine imaging and NIR to have solution. New chemometrics tools, algorithms, combination of NIR signal, information and communication technologies for the successful implementation of NIR in industrial situation, and of course to have decision support system linked to the control board of the plant, because we want to have the information, but also we want to have the decision support system to use this information in a very efficient way. And of course, the new instrumentation, of course, the trend is the miniaturization of the instrument, not only for the industry, not only for the labs, but also for the consumer. I think that in the future, all of us, we are going to have an NIR in our mobile. And the last message, now it's open the 6th edition of the Fundamentals and Application of Near Infrared. This is a course that we teach in my university, in the University of Cordoba, in combination with the International Council of NIR. It's open, and if you are interested, please tell me. You can do the registration until mid of December. And the last thing I would like to present is the sensor field cost-action. This is the European network for assuring food integrity using non-destructive spectral sensor. I'm the coordinator of this long network, big network of people working on NIR and another spectral sensors. Please visit us in the website and follow us in the social media. We have opportunities for mobility, opportunities for training, and also opportunities for conference and workshop. We are very happy to have all of you joining to us in this open network. And this is all. Thank you for your attention. I'm very happy to share with you this information. If you have any question, I'm very happy to answer. I hope I fit to the time. Sorry for going very fast, but I wanted to show. I wanted to say you a lot of things.
Okay. Yeah. Thank you very much, Prof. Lola. Yeah, I think it's very extensive and maybe very comprehensive lecture. Yeah, maybe we need 1 semester to.
Yes.
Usually we need more than 1 semester, but you extract into hours. Okay, I think yes. we have some questions here.
Yes, I have to summarize a course of 20, 30 hours in 2 hours, so it's not easy.
Yeah, it's not easy for some of us who are new, but there are some participants here who maybe who are familiar with NIR. So I think I can. There are some question here, or maybe Iqbal. Iqbal, you want to ask directly to Prof. Lola?
The chat?
Yeah, there is some in the chat,
Okay.
but maybe Iqbal want to ask directly. Iqbal, are you still here?
Yeah.
Okay, Iqbal, you can ask directly. Okay.
Yeah, hello, Professor Lola. This is very interesting for me, since I also get in touch in NIR. But yeah, there are several questions actually that I want to deliver to you. The first one, I still do not have a better idea regarding the difference between the reflectance configurations and the diffuse reflectance. is it only relies on the samples, or there are several things such as sensor probably that can differ that to configurations? I think
Well,
that's the first question.
reflectance is when we analyze the sample in reflectance, what we are measuring is the diffuse reflectance, because it's the diffuse reflectance is the radiation that go to the sample, penetrate a few millimeters, and go back to the detectors, and then we have information about the sample. So when we have an instrument working on reflectance, the information that we have is the diffuse reflectance of the sample. Is clear this now or not?
Oh, okay, so it's depend on the penetrations, right?
Yes, yes,
Okay,
yes. The
okay.
diffuse reflectance is the reflectance that penetrates a bit in the sample and come back. Because if we have just a specular reflectance, it's like a mirror. We don't have information about the sample.
Okay. Yep,
Okay.
yep. So there's no difference on the sensor itself.
No, there is no difference. We talk reflectance.
Okay. Yeah. Thank you. Other things that actually the benchtop instrumentations of NIR, also the software of the Chemometrics is quite expensive. Probably, in European countries, some universities or industry can buy that instrumentations, also the softwares. However, the cases in our home countries in Indonesia, particularly, only several institutions that can have that instrumentations. So according to that, I think I want to ask is about the software. Do you have any recommendation that this is the open source for anyone that can access for chemometric software?
Yes, it's a very good question. We are working now a lot of in developing the same algorithms that we use in the commercial software. We are developing now in Python and also in R software. Because it's true that this is the future, because it's true that the commercial software sometimes are very, very expensive, even for us, even for Europe. And so it's true that we are working now in this. And also, I have to say that I work in a project developed by United Organization for the Food and I don't know how did you say in English, because I'm thinking in Spanish. Sorry, the United Organization for the Food and Agriculture. They are developing a project. In this project, they are developing all these tools in Excel, because Excel is used. So if you need, I can put you in contact with the manager of the project in order to give you access to this Excel course. So it could be useful. But also we are working with one of my PhD students in Python. So also I can provide you information about Python and put you in contact with my student if you are interested.
Okay, thank you, Professor Lola, for your attention and information.
Thank you.
I think that's enough for me.
Okay, thank you, Iqbal. And maybe Iqbal, you can try ChemFlow. ChemFlow, it's free, yeah. ChemFlow, it's free, yeah. Yeah, you can check there. Okay, there's another question. Thank you, Iqbal. There's another question from Johnny Firdaus. Johnny, you want to ask directly to Prof. Lola? Johnny, are you still there? Okay. Johnny is asking about, is it possible to get good prediction only use 1 or 2 wavelength? Univariate, yeah.
Well, I have to say, usually no. Usually no. In the past, when we have just a filter instrument, what we have just a few wavelength, and this was the first approach. But now, when we have the full spectrum, it's better to work with the full spectrum. When we use PLS, that use the full spectrum, we have a lot of comparison between PLS and multiple linear regression. And in all the cases, we have best result with PLS or even the same. So no, with 1 or 2 wavelength, well, if we want to predict something that is very, very easy, it could be, but not for complex application. Okay.
Okay, thank you. And EcoVD, you want to ask directly to Prof. Lola? EcoVD, you there? Okay, basically, yeah, EcoVD.
Yes.
Okay, okay.
Hello.
Hello. Good evening in Indonesia. It's evening. I want to ask about NIR to analyze internal quality of potato seed tuber. I want to analyze about the disease virus that causes the decompose inside it. Does it relevant using NIR instead of using it to analyze the composition, like the starch, protein, etc.? Thank you.
Yes, Echo. I have to say that you could do with NIR. Usually, of course, to develop the model, you have to use NIR and the reference method. But if you use NIR, for example, for we use in many agriculture's application for other studies in pathologies or in development of varieties, is when you develop the application, it's easy to use, is most fast, is faster, sorry, and is less expensive. So I encourage you to use NIR. Of course, you can use NIR for this application that you have described.
Thanks, Proxima.
Okay, it's clear, yeah. So it's very possible to identify disease, yeah, using NIR. So there is another question from Bayu, but I think he's not here. So he asking about using Nir. We want to do measurement on 2 fruit that consists of similar sugar content. When microscopic structure of the 2 fruit is different, how far the difference in microscopic structure affect the measurement? Will the measured sugar content be different due to different structures? So it seems to be that in case there are 2 samples which are similar in sugar content, but the macroscopic, maybe the structure inside the samples are different, will it be the spectra different?
Yes, of course. I have to say that the structure or has a lot of influence in the spectra, because as I mentioned before, we just we don't have just information about chemical composition in the spectra. We have also information about physical parameters, and the structure is very, very, very important. Sometimes for some application that's really are very challenging, we don't know how we can have an answer on NIR, is because we have the effect of this is the alteration of the structure of the product, and this of course affect a lot of the spectra. So yes, we have differences in the spectra when we have differences in the structure of the product. And this is very important. I have to say something for ECHO that maybe, because I was thinking about the question now I have seen here, to analyze a star protein, of course, NIR is very good. To some diseases could be used because you have, again, changes in the structure of the product, but for the virus, if we have changes in the structure, we can use, but if not, we cannot detect microorganisms or virus as all, as we detect using microbiology techniques. I have to say that for this, we have to take care, okay?
Yeah, we have to make sure that because of the disease and the composition of the chemical differ, yeah? Otherwise, yes, it will be the same.
Yes.
If it is the same, we cannot extract information using Nir, right?
Yes.
Okay. Are there any questions from the audience? No? Okay. I think yeah, we have a lot of information from you and it's very interesting. I just want to ask about the reflectance. You mentioned that if we want to measure and we have to make sure that there's no light come out, it means that if I want to use a petri dish, yeah, if I want to do yeah, if I want to measure the reflectance, do I have to make the bottom of the petri dish with the black color or something like that?
Well, it depends on the height of the product that you are analyzing, and also it depends on the packing of the product. If the product is very compact, because usually the light penetrates just a few millimeters. So if the product is very compact, you don't need to put a black bottom cover. But it's not, it will be good to have. If you have a very thin product, or for example, you have, imagine, grains of cereal that have some holes between them, the light could be lost by the holes, so you need to put some black cover in the back of the petri dish or the cup that you have been used.
Okay, thank you. Yeah, I think because we ran out of time. Thank you, Prof. Lola. And here I can see there is our head of department, Professor Lily. Are you here? Are you available to speak? Professor Lily? Okay, maybe he's busy. Okay, Prof. Lola, I think we can finish our lecture today. It is very interesting. I hope that next time, maybe if we have another time to meet directly, or we do Zooming again, we can talk to you, or we can have another lecture from you. Okay. Before we close this session, I think we will have we will give you a virtual certificate. This is a certificate of appreciation from our department.
Thank you.
Thank you very much.
Thank you very much to you.
Okay. And yeah, so for all participants and also for Prof. Lola, I think it is our time to finish the lecture until now, and I will give the time back to the Master of Ceremony. Thank you, Prof. Lola. Give applause to Prof. Lola.
Thank you, Evie. Okay. I hope next time I can be there.
Sure. Okay, thank you.
Bye. Bye to all of you.
Okay, thank you to Ms. Effie who has led the discussion this afternoon. And once again, thank you to Prof. Dr. Dolores Peréz-Marín who have presented the lesson. And for the last, maybe I would like to invite all participants to turn on your camera. We will make a photo together. So please turn on your camera, and when you want to have a picture together with Professor Dolores. Dan sebelum menutup acara, kami meminta waktunya sebentar sesi foto bersama, karena itu dimohon untuk seluruh peserta mengaktifkan video. Okay, I will help for counting to take a picture, and maybe slide 1, I would like to come. 1, 2, 3. Okay, next second slide. 1, 2, 3. And thank you to the participants who have attended this guest lecture until the end of this event. It is reminded again for all participants to fill the presents that has been shared in the chat column, because we only distribute certificate to participants who have filled out the attendance list. Further information can be accessed on our social media. And on behalf of the committee on duty, I apologize if there are many wrong words and actions. The next event is workshop PKKM from Professor Dr. Abdul Rahman, SF, MSI, and Dr. Diding Suhandi, STP, MN, with the title Aplikasi Spectroscopy Visible dan Infrared pada Produk Pertanian on Monday, the 22nd November 2021. Thank you for your attention and participation in today's event. Don't forget to follow our social media account to see more upcoming events. Instagram @tpb.ugm, Facebook or Twitter @tbbugm. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.